The next topic we're going to look at is another important fundamental topic in processing of images, which is sampling and interpolation. Before we go there, we'll quickly review the questions that we left in the last lecture. So one of the questions we asked last lecture was by implementing convolution by going through to a Fourier domain, that is using the convolution theorem, what cost improvement do you really get? Convolution theorem allows us to define convolution in the spatial domain as a multiplication in the frequency domain and then taking an inverse Fourier transform. So you take the individual Fourier transforms of your G and H, which can be your image and your filter or kernel, and then you multiply them and then you do the inverse Fourier transform. Let's take a simple basic case here to explain the cost improvement. So if your image convolution takes order of n square k square times, where n cross n is the image size and k square is the kernel size, then by performing convolution in the Fourier domain, you're still going to have a cost of order of n square for doing a single pass over the image. In addition to that, to do the FFT, you will need order of n square log n square for the image. Recall that when we spoke about the fast Fourier transform, we said that if you have n samples, the cost is going to be order of n log n. In our case, an image has n square pixels, so the cost of computing its fast Fourier transform is going to be order of n square log n square. Similarly, order of k square log k square for the kernel, which is of size k cross k. So together, your computation is going to be of the order of n square log n square plus k square log k square. Any other computations that you're going to have are going to be additive, and this will be the largest component which will overshadow the others. And clearly you can see that this is cheaper than the cost in the original image convolution operations, especially when k gets bigger, which means if your filter size or your mask size gets bigger, using fast Fourier transform to implement convolution is going to give you some cost benefits. A lot of the deep learning libraries that you use today already implement convolution through Fourier transforms. You may not know it. You may just be using a library, a deep learning library, say, for instance, and you just invoke convolution. But the backend of this, many of them already use fast Fourier transforms to implement their convolution, which makes it fast. Okay, the other exercise we had was to match spatial domain images to Fourier domain images. Hope you had a chance to figure out these answers yourselves. In case you had doubts on the answers, let's do the simple ones first. 1 would go to D, that's straightforward. 3 would go to A, straightforward, and we also had that clue in one of the slides in the earlier lecture. And 4 goes to C, mainly because you look at 4, you see a very strong vertical set of edges, and you see that image C has a lot of horizontal edges in the image. So horizontal edges in the original image would lead to a vertical edge in the Fourier transform. Go back and look at the sample Fourier images that we saw last lecture. You will see that we saw an example of a vertical line in your spatial domain, which led to a horizontal line in your Fourier domain, which would be the inverse the other way. So if you had a horizontal line, if you had a horizontal line in your spatial domain, you're going to get a vertical line in your frequency domain. Once again, I think the scope of this course would not allow us to go too deep into the Fourier domains and related concepts. But please do read the links that we shared in the last lecture. Regarding the other two images, which can be a bit tricky, image 2 goes to E, and the reason for that is if you look at image 2, there's a pretty strong vertical line there, and that comes from these horizontal lines at the horizon of the water, or even these horizontal lines that you have in the ripples. So there are lots of horizontal lines in your ripples that's translating to this vertical line in the Fourier image. And the fifth one is a straightforward extension. And the fifth one is, you can see that there are a lot of stalks in the flowers that are giving the horizontal aspect of the frequencies. And there are also a lot of horizontal edges across the different flowers that give you some of these vertical frequencies. Okay, let's review one of the questions we asked the last time again, as to what sense does a low resolution image make to us. If we had to go back and try to understand this from human perception perspective, it is understood today that early processing in humans filters in the human visual system are filters that look for different orientations and scales of frequency. We'll review this a bit more carefully later, but sometimes people also relate them to what are known as Gabor filters. And secondly, the perceptual cues in the human visual system are largely based on mid to high frequencies. So remember, once again, high frequency means an edge, because there's a sudden change in intensity value as you move from one pixel to the next pixel along a row or a column. If it is along a row, you would call that a vertical frequency. If it is along a column, you would call that a horizontal edge. So perceptual cues depend on mid to high frequencies in general. So, but when you see a low resolution image, it is equivalent to subsampling the image. Or if you're seeing an image from very far away, you're actually subsampling the image, which means you may be losing some of the high frequency information, but you do get a lot of the low frequency and frequency information, which is good enough to get a sense of what the object is, but may not give you finer details. So how do you subsample an image as an operation? The simplest way to subsample is, given an image such as this, you simply throw away every other row and column. Consider only every alternate pixel, both row-wise and column-wise. That straight away gives you a half-sized image. You can then go to repeating this to go to lower and lower resolutions. Okay, but if you actually zoomed into these low resolution images or these subsampled images, this is how they look. Right? We're just simply zooming in to these images here. And if you just zoomed in and looked at those images, the half sampled image gets you something like this. The quarter sampled image at a 2x zoom gets you something like this. The 1/8 image at a 4x zoom looks like something like this. Okay, you may ask, say, yes, that's expected. I mean, if you subsample, why do you worry about how it looks at close? That's a valid question, but there's a reason for bringing this up here. Is the last image here looks pretty crufty, right? It has too many artifacts. Can we at least make it look smooth? We understand that by subsampling, you've lost some information, but can it at least appear smooth when you zoom it in is what we are looking for. We understand that you may have lost sharpness, but we still want to make it look smooth. What do you think? How would you achieve this? Okay, let's wait for the answer for a moment, but let's also see another example of an effect such as this. So do you know what is happening in this kind of an image? So this is the original image. We have subsampled in some way and you get an effect such as this. This effect is also known as aliasing. So aliasing generally happens when your sampling rate is not high enough to capture the amount of detail in the image. Okay, we're going to see a couple of examples and then revisit the painting that we saw and how do you ensure that it's not crufty. So whenever your sampling rate is not high enough, you will not get the detail. For example, you see a sinusoidal waveform on top here. If you subsample only at these points, remember that you're not looking at the downward trend of the sine wave. So if you only subsample at these black points, you may think that this is the actual sine wave. Remember here that the frequency of this red wave that we just drew is very different from the original wave. And why is it so different? Only because we didn't sample the original signal. When I say original signal, I mean the one here in purple. Because we did not sample it enough, That's the reason why we end up getting this kind of a shape, which is very different from the original sinusoid wave. So what you need to do to get the sampling right, ideally you need to know the structure of your original signal. And this is where an important concept called the Nyquist rate comes into the picture. We also mentioned this briefly in the previous lecture, but the minimum sampling rate that is required to reconstruct your original signal or to capture the original signal in its actual form is called the Nyquist rate. So now what does the Nyquist rate mean? Nyquist rate goes back to fundamentals from information theory and signal processing, where Shannon, whose sampling theorem is very popular, proposed that the minimum sampling rate or the Nyquist frequency is given by Fs, which has to be at least 2 of Fmax. Fmax here is the highest frequency in a signal. It's the highest frequency in a signal, and we are saying now, and for an image we would say it's an image, and we are saying that your sampling rate or your Nyquist frequency should be at least twice the highest frequency that you have in your image or signal. Okay. Why is this so? We're going to see in a moment, but we can explain the impact of not doing this in an image setting, in a video setting, or even in a graphic setting. Let's see a couple of examples. So in an image setting, if you don't sample your original signal at the appropriate frequency, which is twice Fmax, your shirt is going to look very weird. And this is, as I said, what is known as aliasing. In a video, this is something that you may have observed a lot. Sometimes when you go out on the road, you see a bicycle, especially it happens with bicycles or car wheels. You may, although a car is moving forward, when you look at the wheels alone, it may appear that the wheels are circling backward. Okay, so this could be for a bicycle or a car. Try observing this if you have not already done this. If you have not asked yourself why this happens, here is the reason. Okay. The reason is, if you now take the motion of a wheel to be the top row here. Okay, so the top row here is the actual motion. As you can see in the top row, you can see that the arrow here is moving in a clockwise direction. So you can assume that this is something like a cycle wheel moving in a clockwise direction. But we have chosen to sample it only at 3 locations across all of these. So the top row is the actual movement of the wheel. But these boxes here are the ones that are actually sampled. Okay? They are the ones that are sampled. So if you looked at only the sampled positions, you see that the arrow is first here, then it's here, then it's here, okay, so on and so forth. So probably, in fact, the second and third one could give you the reason why this effect happens. So you see that if you only took the second and the third one, you would actually think that your wheel is moving counterclockwise, because those are the only 2 samples you have, and the arrow is moving in the counterclockwise direction. But originally your wheel was moving in the clockwise direction. This simply means that you're not sampling the wheel at the frequency at which it's rotating, right? or at twice the maximum frequency at which it's rotating. Here's another example from graphics, and the reason is again the same. You can see in this particular case that the aliasing is prominent at these regions where the frequency is very, very high. Okay, remember, once again, when we say frequency in an image, we mean how quickly the pixels change between black and white. When we say black and white, it can be dark gray to light gray, but going from black and white, and that becomes very high closer to the horizon of this image, and that's where the frequency is very high, which means your sampling rate has to be twice that frequency to be able to be true to the original image. And this is an effect that we often see with graphics. Okay, a more tangible way to understand why you need to sample at twice the maximum frequency. We are not going to derive Shannon's sampling theorem here, because that's not the focus of this particular course. But let's try to intuitively understand why you need to do sample at twice the maximum frequency. Let's take this example of a chessboard. Right? So you have a chessboard here, and we argue now that the top row are two examples of good sampling practices, and the bottom row are bad sampling practices. So let's see here that if you see this one here, that's the bottom left, you can see that the samples are these circles here. Okay, you can see those circles, and when you see those samples, you can clearly see that we are sampling all of them at only blacks. So if you had only those 4 samples, you're going to assume this entire board is a black board, that there are no white squares in between, because you never sampled in the white squares. So clearly you're not sampling at the appropriate frequency here. The frequency here is how quickly does white and black change, in how many pixels does it change. Clearly you're not sampling at twice that maximum frequency, and it's going to give you poor information. Here is a slightly better sampling, but still not complete. So once again here you can see these hollow circles. You can see that you improved your sampling a little bit, but once again you see a black, you see a white, and again your third sample on that first row is a white again. So which means your perception or any further processing is going to imagine that this is black followed by a series of white. That is not checkerboard or a chessboard, but it's just an entire block of white after the first small square of black. It's an entire block of white, which again is poor sampling. So here is a sampling where we actually go at twice the frequency. Okay, you may ask why twice. So in this case, remember here that the actual frequency is when a signal completely goes through between its variations. So in this case, a signal completes from here till here, and we are sampling twice inside those 2 boxes. So which means we're sampling at twice the maximum frequency. And when you sample like that, you've got a sample in every black square and every white square, and you now know that this is a checkerboard. Obviously, if you sample more than that, that's even better for you. Hopefully that gave you an intuitive understanding of why you need to sample any signal, any image at least twice the maximum frequency of content in the image. So a good anti-aliasing technique is Gaussian pre-filtering. Okay. We'll talk about what Gaussian pre-filtering means in a moment. But this is the image that we saw earlier. We said that this image was crufty, and this is what we want to try to achieve. We do understand that if you subsample, you're going to lose some information, but we at least wanted to make it look smooth. So how do you do Gaussian pre-filtering? You're first going to take an image and then do a Gaussian blur on it. Okay. You know now what a Gaussian blur is. It's Gaussian smoothing. You can take a 3x3 Gaussian kernel. In case you don't recall what a Gaussian kernel is, remember it looked something like this. At least a 3x3 Gaussian kernel looked something like this. Okay. And you also had a 1/16 to normalize it, and that was your 3x3 Gaussian kernel. Similarly, you can also build 5x5 kernels and so on and so forth. So you first apply that kernel on your input image. That gives you a blurred version of the image. Now you subsample. Then before you subsample, again blur, then subsample, blur, then subsample, blur, then subsample, so on and so forth. Why do you think this works? There's a reason for this. Okay. Let me ask you this question. This, as we said, is a Gaussian filter. Do you recall what a Gaussian filter is? A low pass filter or a high pass filter? A Gaussian filter is a low pass filter, which means it removes high frequencies and only passes through the low frequencies, relatively lower frequencies, which means it's going to remove, remember, any smoothing filter removes a certain amount of high frequencies. So by applying the Gaussian blur, you've removed the high frequency, which means your sampling rate now can actually be reduced. Remember again, the Shannon sampling theorem states that you must sample at least twice the maximum frequency in the image. if I reduce the maximum frequency in the image, I can sample at a lesser rate. And that's the trick that we employ to be able to subsample but still have a smooth effect in your output image. So you do a Gaussian blur, now your overall frequencies have come to a smaller range. Now you can afford to subsample without having an aliasing effect or cruftiness in the image. And that's what we mean by Gaussian pre-filtering. Okay, so now subsampling is one side of the story, and the other side of the story is how do you upsample? Sometimes you need to go from a low resolution image to a higher resolution image. And the simplest way to do this would be a very standard interpolation operation. Right? An interpolation between any two values. So you have, let's say you're talking about the real axis. The interpolation between any two values here is simply values that lie on the line connecting, at least linear interpolation is on the line joining those 2 points. Okay. So the simplest form of interpolation that we can do if we want to upsample an image is what is known as nearest neighbor interpolation, where we simply repeat each row and column 10 times. Right? So every pixel, you repeat it 10 times along the column and 10 times along the row. So it almost becomes like one entire 10 by 10 block has exactly the same value. Then you take the next pixel, repeat it for 10 columns, repeat it for 10 rows, which means the next 10 cross 10 block has the same value, so on and so forth. Good news, your resolution goes up. Bad news, you're going to have such artifacts across the image because this is exactly what you did. Because you took several blocks, several pixels and simply expanded them into blocks. How can we do better than this? Right? Clearly, we do not want to upsample images like this and have a blocky effect in the upsampled image. So the way we can go about doing interpolation or upsampling while retaining some smoothness in the output is, let's try to recall how a digital image is formed again. Recall an image being a discrete sampled version of the original continuous function, right? Or the original continuous signal. So you have an original signal f, you quantize it at certain locations, which gives you your image or your signal capital F at XY locations. Right? In our case, it's going to be an image. So as we already said, this is nothing but a discrete point sampling of a continuous function. So when we do interpolation, we are simply asking the question, can we somehow reconstruct that original continuous function from the discrete samples? That's the question that we are trying to ask, because if we could do that, we could interpolate and go to any resolution that we want to go for. Unfortunately, in practice, we do not know the small f, which is your continuous function. Right? We do not know that continuous function. We do not know how, what was the real world scene from which your image was captured in a sampled manner. However, we can try to approximate this in a principled way, and the way we are going to do that is through a convolution approach. Okay? So the first step that we want to do is convert your continuous function, convert your f, which is your discrete sample version, to a continuous function. Because we do not know the original continuous function, we're going to define a pseudo continuous function, which simply states that wherever you know the value, you simply put the image's value there. Everywhere else, you just say it is 0. This would be an automatic version of a continuous function. This is at least a continuously defined function. Let me put it that way, at least for the moment. So we now try to reconstruct your f hat, which is the resolution at which you want to take f2, right? By convolving this pseudo continuous image with some filter. So we want to ask if we have some, okay, this is not exactly right in terms of the function, so let me erase that. But if we have this function, continuous function f sub capital F, can we get some kernel h in such a way that we can construct your original, not original, but at least an upsampled signal? What do you think h should be? Okay, this image should give you some understanding. maybe a signal such as a tent in a shape of a tent could help you with a 1D signal perhaps, but that still doesn't answer how convolution can take us from one resolution to a higher resolution, because the way we saw it, convolution can maintain the same resolution if you include padding, and if you don't pad, you probably will lose a few pixels on the boundaries. But now we want to go to a higher resolution when we use convolution. Now, to be able to perform interpolation and then upsample an image to a higher resolution using convolution, we're going to do it using an interpolation kernel, which is defined as what you see here. Remember again that your original convolution is defined something like this, where you have g of ij is equal to summation f of kl into h of I minus k j minus l. And this is the new definition that we're going to use for interpolation. And if you observe carefully, the main difference between these two expressions is the quantity r here that's multiplying k and l, and r is what we call as the upsampling rate. Right? So if you want to double your image, your r is 2. If you want to quadruple your size of your image, remember we are doing upsampling. So if you want to quadruple the size of your image, r is going to be 4, so on and so forth. Let's try to understand how this actually works. Let's, just for the sake of simplicity, let's look at one-dimension variant of this. Let's say g of I is equal to summation over k f of k into h of I minus rk. Okay, that's the one-dimensional variant of the same equation. Remember once again that an image is a 2D signal for these purposes. So a lot of these expressions that we write for images, if you remove one dimension, you can apply that as convolution for one-dimensional signals. Okay, so this is what we actually have in one dimension, so it's just easier to explain in one dimensions. So let's try to understand what's actually happening, right? So let's consider an x-axis. So let's assume that there are some signals f of k minus 1. Let's say there's another signal f of k, and there's another signal here f of k plus 1, so on and so forth. This is very similar to what you saw on the earlier slide, right? So I just drew lines such as these to represent the various values of f that I have with me. That's my input image, which I want to increase the resolution of. So now, because I want to increase the resolution, the question that I'm asking here is, if I take some I here in between those values, what would be g of I? Remember, g is the output, f is the input. Okay, that's what I'm trying to ask. So in the g axis, the tricky part here is that the coordinates, the indices in g are different from the indices in f, because f has only a certain number of indices, whereas g has double those number of indices. And so this would be r into k minus 1 in g indices. This would be rk, and this would be rk plus 1 in the indices of g. Now if we try to understand what g of I is trying to do here, it's the summation of fk into h of I minus rk as you take many k values, right? So of course k can range from k minus 1 to k plus 1 if you take a 3x3 window, or a higher, depending on k simply defines the length of the window that you have. So in this case, so what we mean now is h of I minus rk. So if you again took an example such as this, remember here that h was one of the interpolation kernels. In this case, it's called a tent kernel because it looks like a tent. And what this kernel does is, as you go further out from the central pixel on which you place the kernel, the effect of those pixels fall off linearly, not exponentially, but linearly, right? So that's what is your tent kernel. So if you add a h such as this, you're simply saying that this f, so if you place the h kernel here, so if your h kernel is placed something like this, okay, so then you're saying g of I is going to be f of k into h of I minus rk. I minus rk is this value here. I minus rk is going to be this value here with respect to h, which is the green curve. So you're going to multiply fk by h of I minus rk, fk plus 1 by h of I minus rk plus 1, which is going to be this quantity here, so on and so forth. So by doing this operation, you are able to interpolate, and you'll obviously sum up those values. There's still a summation here. You'll sum up those values, and that will give you what the value of g of I is. Okay. That's how these interpolation kernels work. So now a linear interpolator is what we saw, corresponding to a tent kernel. You can also have more complex kernels such as B-splines. Those are one of the most complex kernels. But here are some qualitative results of applying this interpolation. So the first one that we already saw is an effect of doing the nearest neighbor interpolation, where you have the blockiness effects. Then if you do bilinear interpolation, which is the linear interpolation that we spoke about, but along the two axes, then you get something like this. If you go to bicubic interpolation, you get something like this, so on and so forth. So the main difference in these interpolations is the H kernel that you use. In one case, it's nearest neighbor. In the second case, it's bilinear. Third case is bicubic. We're not going to define every kernel, but you can look at the references at the end of this lecture to be able to understand various kernels that have been defined in practice. So just like how we defined interpolation, you can also define the complementary operation of it, which is decimation. Decimation means subsampling. So which means while we saw subsampling so far as simply omitting every other pixel, where if you do Gaussian pre-filtering, you also ensure that you get a smoother output. You can also achieve subsampling using a convolution-like operation, where it would be very similar. The only thing is, instead of rk, you're going to have k by r and l by r here, because you now want to subsample and not interpolate. So that's where we're going to stop this lecture. To know more interpolation kernels and decimation kernels, you can look at these references that are on your homework. Please read them to understand these better, and we'll continue with the next topic.